Hello and welcome back. In this slice of physics, we're going to discuss free fall. Free fall is something we have all seen around us. These are when objects in our day-to-day experience fall to the ground. We're going to see how free fall is just a special application of a constant acceleration motion that we have been discussing lately. Moreover, it continues to be a one-dimensional motion as we have been talking about, except that this time the dimension along which the motion occurs is the vertical axis, which is generally referred to as the y-axis, and a lot of our examples up to date have been dealing with the x-axis, or horizontal motion. And we'll take an example problem of a free fall. So we're going to discuss free fall motion in the context of this example problem, which states that a stone is dropped from a balcony 20 meters above the ground, and it asks us how long does it take to hit the ground and with what speed does it hit the ground. As always, the first thing you want to do in solving a physics problem is draw a picture that captures the question and the situation. So here's the balcony, and a stone is held outside the balcony and let go or dropped, and it falls to the ground and hits the ground. Let's say that's here. It tells us that the stone falls a total of 20 meters, so we can mark that here. And so there's our setup. Now before we solve this problem, let's just quickly review some of the key concepts around free fall motion. So what is free fall motion? When we let go of the stone, why does it fall to the ground? Well, you all know that it does that because of gravity. So falls due to gravity. But what is gravity? Well, it turns out it's two things. There is a force of gravity, which we will discuss in a few weeks. We haven't gotten to forces yet. And one of the ramifications of the force of gravity is that there's an acceleration due to gravity, which is what we're going to talk about now, since that is a topic that we have been discussing lately. And the acceleration due to gravity, for some of you, it would be a familiar term, and for some of you, it's a new term, but that's all good. The acceleration due to gravity is written as a lowercase g. And we know from experiments as well as from theory, and we'll discuss some of this more a little later, that the acceleration due to gravity near the surface of the Earth is 9.80 meters per second squared. And that gives you the magnitude, and since we know acceleration is a vector, we got to specify the direction, and the direction points straight down. Okay, with those concepts in mind, let's see if we can start setting up the solution to this problem. So once we have a picture, the next thing that's good to adopt in most physics problems is a coordinate axis. And in this case, since the motion is vertical, the axis that we are concerned about is the y-axis. So let's just show that over here. This is the y-axis. The position of the stone at the beginning here when it is let go is the initial y position. The position when it hits the ground right here is the final y position. And if we set up our coordinate axis with 0 at the ground, and so if this is 0 here, this would be plus 20 over here as my initial position in units of meters. So let me show that over here. Okay, once I have this much set up, let's see if we can start listing some of the things that we know. My initial position, yi, is plus 20 meters. My final position, yf, is 0 meters. My initial velocity, we do know that even though it looks like that's not specified in the problem, but when the stone is dropped, it is not thrown. It's just simply let go, which means the initial velocity immediately after I let go is going to be 0 meters per second. The stone starts to drop from rest. That's an important fact. And then we also know the acceleration in the y direction. Because this is a free fall, we have the acceleration due to gravity in play, and the acceleration in the y direction is going to be minus 9.8 meters per second squared. The reason it's negative is because our y-axis points straight up and the acceleration due to gravity points straight down. So even though g, the little g, is always a positive value, a lot of times, depending on how we set up our coordinate axes, the acceleration in our y-axis could be negative if the y-axis is set up like it is here with positive pointing up. Okay, that's the information that's given to us, and the two pieces of information that we are being asked for are what is delta t, the time duration, and what is VF. So once we have set the problem up this much, then we can look at the equations. So let's bring in the equations of constant acceleration motion. So here are our four equations of constant acceleration motion as we have discussed them before. Here I have the sense of direction as delta x. Now we will be using delta y instead, and some of the subscripts would be y instead of x. So this vi is technically vyi, and this vf is technically vyf. So we can figure out either of these first. Let's just go with delta t. To get delta t, can I use this second equation here? It's got delta t, but I don't know VF, so that's not useful to me. I couldn't use the first equation because this delta V is VF minus VI, and I don't know VF again. So I got to use this third equation. And in our case, this third equation translates to be delta Y equals VYI delta T plus 1/2 AY delta T squared. And as I said before, these are VYI and VYF, even though I didn't specify them when I first wrote them. So now delta Y we know is simply YF minus YI. So this would be 0 minus 20. Delta, remember the change is always final minus initial. And that would be equal to VYI is simply 0 times delta T plus 1/2 AY is minus 9.80 meters per second squared, and I got delta T squared. So this term here goes away. 0 times any delta T will simply be 0. And so this is simply minus 20 equals minus 4.90. That's what 9.80 divided by 2 is, times delta T squared. And if I divide both sides by minus 4.90, I will get delta T squared equals minus 20 divided by minus 4.90. The negatives cancel, and delta T in seconds would simply be square root of 20 divided by 4.90, and that turns out to be 2.0 seconds down to 2 significant digits that some of our inputs were. So that's how long the stone dropped from a height of 20 meters, which by the way is about 60 feet, so I'm dropping it up from about the 6th floor of a building, and it drops to the ground in just 2 seconds because its acceleration due to gravity is pretty high. So the last thing I want to solve is VYF, and now that I have delta T, I can simply use the second equation over here and set up VYF equals VIF plus A times delta T, or rather AY times delta T in this case. So now substituting the values, I will get VYF equals, once again, 0 for VIF plus A is minus 9.80 meters per second squared times delta T, which now is 2 seconds, which gives me an answer of minus 19.6 meters per second, or down to our 2 significant digits, minus 20 meters per second. And there's our answer to the second question. The negative makes sense because the velocity is in the downward direction when it hits the ground. So in our coordinate system, that's a negative value. Now, a couple of quick things I want to point out here. Number one, instead of using the second equation and using our new delta T, we could have used the fourth equation and simply using the values of VYI, which we know, AY, which we know, and delta Y, which we know, we could have determined a value of VYF. And you can do that as practice for yourself and find that you will get the same answer. Secondly, the fact that we get a final velocity that's not 0 confuses some students. Some of you are thinking that once the stone hits the ground, eventually it comes to a stop, so the final velocity should be 0. Well, when we set up a physics problem, it's very important to know what time duration we're solving and what our initial and final conditions are. And in this case, since we are interested in finding the speed with which the stone hits the ground, that is the final position. not what happens after that when it bounces and eventually rolls to a stop. So in this slice of physics, we looked at free fall motion as nothing but a special application or a special case of constant acceleration motion along the y-axis, and we took an example problem of a stone dropping to the ground to see how all that works. Thanks for watching.